Yes, sir, I recall. I started.
So, good morning, everybody. I understand that many of you may be having slight difficulty because of the power situation. We are recording it, and if required, we'll redo a bit of it again. So, we are in dynamic programming, and there our main aspect to consider are identical subproblems. And in order to handle identical subproblems, we do what is called remember and reuse. And therefore, our whole algorithmic steps are as follows, is that from the recursive definition, you create an optimal substructure because many of these problems are optimization problems. And then when we start evaluating this structure, because of the identical subproblems, we memorize. So in addition to our recursive decomposition, base condition, recursive decomposition, uh, recursive calls, recomposition, we also have reuse and remember. We also saw that there are two kinds of methods here. One is the top-down method, which is directly taken from the recursion, and then from there it moves on into remembering. So we store some global information data structures to remember things and we reuse them. In many cases, we can see that the whole problem can be indexed in an efficient way. And because it can be indexed in an efficient and effective manner, we may actually be able to go ahead and uh, do an iteration. So we call it a bottom-up iterative approach, and in some cases we may need to use special data structures. So today we will start discussing two classes of problems, basically one class which is related to string matching. There are two basic problems in string matching. The first you'll all know, which is the pattern matching in a text. That means we have got a string or a text of characters. We have got a string or a text of items where, and we have got a pattern P, and we want to find out the occurrences of P in S. This match could be an exact match or could be an approximate match. An approximate match may assume one error, two errors, one difference, two difference, etc., etc. The first and the original problem is the exact match problem. Take this example. S is A, B, A, C, A, B, A, B, A, C, A, A, and pattern P is A, B, A, B, A, C. Now we know that the string A, B, A, B, A, C has this match. I think power has been restored. Can you check, Chandan?
Yes, sir.
Has power been restored?
No, sir, not yet. Like I am in
No,
hostel,
sir,
so
not yet.
Right. Okay, fine. Amatya, can you check whether power has come back?
It's
Sir,
not yet.
in my place it has come back actually.
In some places it is coming back, so it will come back. So this is the match. This is the pattern and it matches the string here. The matches could overlap and there could be multiple matches. For example, if the string is A, B, A, B, A, B, A, C, then and the pattern is A, B, A, then you can see that there is one match here, there is one match here, and there is another match which is here. So matches could be overlapping, and these are exact matches. Sometimes we are also interested in approximate matches, especially when you do a typo or a typographical error, then you may end up in approximation matches. That means there could be one difference, two difference, etc. etc. And we will discuss those under the class of what is called edit distance. So approximate match often comes up in the class of problems called edit distance, and we shall discuss that today in today's class as well. The other very interesting category of problems is the sequence alignment problem. The origin of the sequence alignment problem came from protein alignment. And you know that proteins are mapped into this ATCG, which are various components. And what we try to do is find an alignment. So what is an alignment? Let us look at the two strings X and Y. In the two strings X and Y, we find out that this pattern NTRACT, this is there in sequence here, though there may be some intermediate elements. Similarly, NTRACT is also there in Y. So here we find out that there are sequences which match, but they may not match in the intermediate portions. They will match in some subsequences. So some subsequence of one will match with some subsequence of the other, but they may not match in the full sequence. That means similarly, other than NTRACT, CTI. Look at CTI. CTI is here and CTI is here. CTI. Similarly, NTRAI is also matching. These are the longest matches of its kind. Obviously, NTRA is also a match, but there are larger matches than NTRA here. For example, NTRACT, NTRAI. So these are called maximal, not maximum, but maximal. That means they cannot be extended any further to form a match. Here, our interest is either to find all matches of length greater than equal to k, or to find the longest possible match. The longest possible match is the famous problem called the longest common subsequence problem. It's a very famous problem in computer science and it is used in many places. This longest common subsequence problem is also used for protein alignment. And as I said, in the more general sense, we use what is called edit distance, and we shall come to it subsequently. Anybody has any questions at this point? If there are no questions, I will request you to now solve this problem. Given a string of characters and a pattern P are two strings, I want to find out the first occurrence of P in S. So write down the recursive definition. The standard algorithm that we have, please write down the recursive definition and tell me what would be the recursive definition. Or what would be your any algorithm that you would do? But I think it is good to start from the recursive definition. Then you will really get into an appropriate mechanism. So what would be the function arguments of the recursive definition? Can anybody tell me what would be the arguments?
So find match, so we will return an index, which is the start of the substring, and the function would have arguments, the string s, the string of characters p, and the index from which we'll start the search. So we look at the first element, and if it does not match, then we recursively call the function on the shorter sequence of s.
And if it matches?
So if it matches, then we call it on we shift the point. We call it on the smaller sequence of s, and we also decrease the p. So
correct.
We call it on s plus 1 and p plus 1.
Got it. Omi Katrodia, have you got what is to be done? Mayank Vaid. Manish Kumar Roy. Kumari Bhavna.
Yes, sir.
Can you tell me what your classmate Ishan just now said?
Sir, I just went out to take water actually. Just came.
So you have not paid attention to what we are discussing?
So I was listening, I just went out to take water.
Karthik Sahu?
Yes, sir.
Can you tell us what Ishan said?
Sir, I couldn't follow, but he told that we'll be returning the index.
Do you know the problem that we are solving?
Sir, we'll be finding the first occurrence of P in string S.
Correct. So how would we do a recursive definition?
Sir, we'll be finding the index of the first index in S of P, and then we'll be returning that.
How? What is the recursive definition?
Sir, I'm thinking on that.
Okay.
I couldn't follow what.
Abhishek Gurjar. Abhishek Gurjar. Piyush Jangid. Ritik Mishra. Lathia Deep Mahender Bhai.
Yes, sir.
Can you tell us?
Actually, I also couldn't follow what Ishan said. But
no, can you think on your own? Forget
that,
about following. Do you know the problem that we are discussing?
Yes, sir.
You are aware of the problem. So how would you solve the problem?
Yes,
what would be the arguments of the function? Suppose I want to call it match. Sorry.
Sir, we can find the first index of P in S.
Arguments
then
of the function.
If the
what
so
would
the
be
index
the arguments
first
of
the
the
index.
Function? What would be the arguments of the function? I'm asking you a question.
So that the string S and P.
string S and P?
Yeah, and the first index of P.
The first index of P is P itself, isn't it? No.
Yes, sir. Yes, sir.
Then what would you do? What is your base condition?
If the length of S is less than P, maybe.
Length
Then
of
we couldn't find
S.
the.
Length of S is less than P. Then what will you return?
We return the null.
Null. Then what else?
If the length are same, then
Then
it should not be the base condition because there should be no matching also.
if the lengths are same, then
No, sir. It's not a. It should not be a base condition if the length are same.
Okay. Think a little more.
Okay.
Gaurav Jha. Druhin Abrol.
Yes, sir. Sir, I was thinking we can check the first element of S with the first element of P. If then it matches, we can remove the first element of S and then recursively call it again. And if it does not match, then we can just increment the index of S and we can call it so that it starts comparing from the first index.
Correct. So this is exactly what Ishan said. There are two parts in the recursive condition. So S1 is equal to P1, then S1 is not equal to P1. This is what you said, isn't it?
Yes, sir.
So if S1 is equal to P1, you will call it on what?
What, sir?
If
S2
S1
and
is
P2.
equal to P1, you will call it recursively on what?
S2 and P2.
Not S2, that means S minus S1, isn't it? And P minus P1. And if it does not match, what will you call it on?
Sir, S minus S2 and
S minus
P.
S2 कहाँ से आया? You have only checked S1 and S2. S1 and P1.
So S minus S1 and P.
And P. Correct, correct. So this is one case and this is the other case. Ishan, these are the two cases you also mentioned?
Yes, sir.
And the base conditions are if pattern size is less than string size, then you return false. And if pattern size is equal to string size and both exactly match, then you return true. This is one way. There are other ways to do it.
So,
yes.
So, or maybe we could just say that if the pattern size has become 0, then you should return the index. So we could have another argument.
Correct, correct. If pattern returns 0, is become 0 and string is still there, then you have found the match. Good. So this is the definition. As you just said, that you have two strings, the string S1 to Sn, the pattern P1 to Pm, and then you match S with P. And if the size of S is less than the size of P, returns 0. This one just returns true or false. Otherwise, if P is 0, then you return 1. And then you check if S is equal to P or not, S1 equal to P or not. And then if you want to find all matches, then you call both. Or do you call only, suppose the first one matches. Here, remember, whosoever told me about this, suppose the first one matches, will you call only on this one or will you have to call on both? If the first characters of S and P match, will you call it on both? Will you call only this recursion R1 and will you not call it on R2? Or will you call it on both?
So we will call it on both.
Yes, very good. You'll have to call it on both
So
because
what is R1 and R2?
the first one may not return true. So if S1 equal to P1, you call it on both. If S1 does not equal to P1, then you call it only on one. And you initialize, you get one value in X, the other value in Y, whose both values you have initialized to zero, false, 0. And after you get X and Y, you return the OR of X and Y, which again returns true or false. If you want to return the index, then you have to maintain something else. Is it clear to everybody else now how we have done this?
Yes, sir.
Lathia Deep Mahendrabhai, is it clear to you? I cannot hear you.
Hello, sir.
It is clear?
Yes, sir, clear.
Kumari Bhavna, is it clear?
Yes, sir.
Okay. What is the complexity of doing this? What is the complexity? What is the recurrence equation? What is the recurrence equation for this? How would you write the recurrence equation? T what?
Sir, is it coming from both the string length?
T of n comma m is equal to?
T of n minus 1 comma m minus 1 plus T of n minus 1 comma m.
Plus 1. And in any case, you can see that this, in the worst case, this is only the recursive part. There are base conditions to this, which is determined by the base conditions if m is less than. So because if m is equal to 0, then also it becomes something. If size of m is equal to size of n, also we know. So the base parts have to be written. And we can all see that this is an order n into m algorithm, which you can implement by a 2 for loops, isn't it?
Yes, sir.
Yes, sir.
Now we will see what sort of memoization and data structuring we deploy so that we are able to get an efficient algorithm. Please pay very careful attention. Are you all with me? Say yes or no loudly.
Yes, sir.
Yes, sir.
Thank
Yes,
you.
sir.
Yes, sir.
So I have
Yes.
one question.
Yeah.
So what does the algorithm do if S1 is not equal to P1? So even
It
in
does
that
only
case,
the
we should
second
be
part. This
Oh,
S1
okay,
equal to
sorry.
P1.
Yes.
This bracket started here and ended here, Baba.
Sorry, sir. I did not notice. I'm sorry.
Can you see now if S1 is equal to P1, the bracket starts here and ends here.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
And therefore it does both. After it completes that, it does Y, it calculates Y. And if S1 is not equal to P1, also it calculates Y. And I have initialized X and Y to 0. Clear?
Yes, sir. Yes, sir.
So now we do a wonderful memoization. And this wonderful memoization is to create a tabular structure, a tabular data structure, which is also called a deterministic finite automata. Don't bother about it if you don't know. How many of you know what is a deterministic finite automata? Please raise your hand. Okay, don't bother. Look at this purple colored conceptual structure. This, sorry. This is the start of, so taking the pattern P, I create a data structure. And this data structure tells me what I have to remember to go where while I'm scanning S. What I have to remember is where am I in the pattern so that I don't have to start again from S. Where am I in the pattern so that I don't have to start again from S? Are you all with me? Please say yes or no.
Yes, sir.
So at the start point, I say that if I have got A, then if at the start I have got A, then of the pattern, I have moved one step. If I get B or C, then I remain here at the start. That means, why have the students decreased like this? Why have the number of students reduced like this? Is somebody removing the students?
No, sir. Actually, I'm making them the attendees, so you can see them in attendees.
Okay. Okay. I cannot see the attendees. That is the problem. Let me see. Okay. Got it. Okay, got it. Thank you. So now, if at the start I get A, I know that I have moved one step. So I call it one step movement. I am at index 1 from index 0. If I get B or C, I remain at index 0. So now all of you tell me that if at index 1, I get A, which index I remain in?
1.
1.
So 1.
If I get B, which index I go to?
2.
And if I get C, which index I go to?
0.
0. So now you can see how I am moving. Now look at this diagram very, very carefully. And in B, in index 2, if I get A, I move to which index?
3.
And if I get B, I move to which index?
0.
0. And if I get C, I move to which index?
0.
So
0. So now I know how I am going to move from one to the other. And because I know how I am going to move from one to the other, I am going to create this data structure by pre-processing pattern P. Having created this data structure by pre-processing pattern P, now when I scan the string S, how many times will I will go back and forth on the string S?
So just once.
Just once. So now I have converted a quadratic algorithm to a polynomial time algorithm just by creating a data structure. Just by creating a data structure. Is that clear? Is that clear to all of you? Can you all hear me? Hello?
Yes,
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 you are
sir.
audible.
Yeah, I'm audible, but is my screen also visible? Because I lost one connection, but I think you all can still see the screen.
Yes, sir.
Okay, good, good, good. So this is the most interesting thing that I have done. And this method is of data structuring and remembering is developing some of the classical pattern and string matching algorithms that are known, one of which is the Knuth-Morris-Pratt algorithm. Just wait a minute, I am getting a problem in this connectivity. So let me try and join again. So you just hold on for some time. I am unable to connect from my other device, so I will have to stop this. I'm not even able to stop this presentation because I'm changing my screen. I'm writing on the screen, but nothing is happening. So I'm going to sign out and sign in again. OK. Can you all hear me now?
Yes, sir.
Yeah, it seems I'm unable to connect from the tab which I was using. So I will go back and try to work it out from another device. Just hold the line. I will try to just connect with another device and start doing the stuff. Just hold on. I will. I lost my connection for some reason on the tab. Just bear with me a little. Can you see my screen? Tab screen? No.
So we can see the presentation.
You can see?
Yes, sir, we can see the presentation.
You can still see the presentation.
Yes, sir.
Sir, I am not able to see anything.
Can you see anything now? None of you? Any of you?
The PPT slide is still visible for me.
That old
Yes,
PPT
sir,
slide.
even for me.
Can you all do one thing? Can you all please log in and log out for a moment? Sign in and sign out and sign in. There's some problem here.
Sir, if I rejoin, I can't see the slide.
So I will ask you all to rejoin.
Okay, sir.
Okay, sir.
All of you please rejoin and I will try to.
Sir, I have rejoined, but I still can't see the slides.
No, I have not yet shared it.
Okay, sir.
I guess the screen is still not visible, isn't it?
Yes, sir.
No, it is not visible.
It is not visible. So let me do something else. There's something wrong that is happening. So let me try something else. Can you hear me now?
Yes, sir.
Yes, sir.
Wait, let me try now to see whether this works. Just all of you hold on for some more time. I have to try from another device, so it will not work. Just hold on. I will get back. Are you able to hear me? Is my screen visible? Not yet, no?
No, sir.
I am unable to share my screen. I don't understand why that is happening. They are not allowing me to share my screen for reasons unknown to me. Is my screen visible now?
No, sir.
No, sir.
That's funny. I'm really. Somehow I am not. Palash?
Yes, yes.
If I send you the slide,
Yes,
can you share it?
Yes, I can share. Yes, yes.
I'll mail it to you just now.
Yes.
Just check, I have mailed.
Yes, it is yet to come, I think.
Okay, it will come.
Yes, it has come. Let me share it.
I'm having more serious problems.
I don't know. There is some problem. Yes, yes. Now it has come. Yes, I have shared. Yes, now it has come. Yeah. So what should I look at? 15 page. Oh, 15 page. Yeah. Which page I should go? This one we were discussing, right?
Yes, sir.
Okay.
Are you all with me? Hello?
Yes, sir.
Yes, sir.
Okay. So as we are trying to see that this pattern and string has reduced the complexity of the problem from an order n into m to order n plus m. This is a classical example of using dynamic programming and data structure. Olash, we can go to the next slide. Yeah, now we come to the next problem, which is the longest common subsequence problem. As I had discussed in the previous few sessions, is that here we are not interested in an exact match. Rather, what we are more interested is in a match where the sequences match, but some of the intermediate elements need not match. Because some of the intermediate elements need not match, therefore, we will now move on to a newer concept. So if you see the examples that we did, where we had interaction and contradict, and there were three places of maximal matches: NTRACT, NTRAI, and CTI. Are you all able to see that? Are you all in a position to see that? Can you confirm, please?
Yes, sir.
Yes, sir.
Yes, sir.
And in the next one, when you have S1 and S2, can you list out which are the places where they will match? I have already listed CTAATA, but any other matches possible?
So GT can also be a match. So is there a minimum length which we should take?
No, you have to take a string which matches, after which you cannot add anything else to match. See, for example, if you take GT, then you will see GTT also is there, GTTT is also there, GTTTA is also there, GTAA is also there. Have you got it?
So the another LCS would be TTTAA.
TTTAA. Correct. 3 T's AA. Perfect. 3 T's AA would be another LCS. So now my question is that given a string length, I want to find the longest common subsequence. So how do I find the longest common subsequence? So all of you please write down and put the answer in the chat box.
Sir, I had a question regarding the pre-processing step of the tree.
Has anybody written in the chat box? Palash?
Yes, I have gone
Palash?
to the slide. Yeah.
Yeah. So all of you see the solution. I'm sorry it's going on this way because 3 of my devices have crashed. So I'm in real trouble. So don't worry, we'll find a solution. So if you see the solution, then you will see that the recursive definition has got 3 parts. The first part says that the base conditions are if x is null or y is null, return null. Otherwise, when x is x1 to xn and y is y1 to ym, then if x1 equal to y1, then what do you have to do? Can anybody tell me?
So we can include x1 into the common subsequence and
Yes, x1 or y1 into the common subsequence and call it recursively on x minus x1 and y minus y1. Correct? Is it okay with everybody? Ritik Prabhakar? Ritik?
Yes, sir. Got it, sir.
Otherwise, you will either delete x1 and call it on x minus x1 y, or you will delete y1 and call it on x y minus y1, and you will get the maximum of z2 and z3. And you will return either z1 if x1 matches y1, and if it does not match, then you will return from the other two sides. Is it clear to everybody how to do it? It is a slight variation of our pattern matching problem. Where if the first two characters matched, then we consider that to be part of the longest common subsequence and called it on the rest, and whatever we got from the rest, we added it to it. We will add it to it. Otherwise, We call it on LCS x minus x1 y and LCS x y minus y1. Will we add anything here? If we call it on these, any one of them, will we add anything to the common subsequence? Will we add anything from there? Yes or no?
Sorry, sir.
Will we add? See, in when we did Z1, we added, we said X1 concatenation of that, isn't it? That means X1 was added to the.
Yes.
But when we do Z2 or Z3, do we add anything to the solution?
No, sir, we do not. No, sir.
No, sir.
Because
no, we don't. So is everybody convinced that this will yield the longest common subsequence? Yes or no? Who
Yes,
has a
sir.
doubt? No, those who are yes is fine. Anybody who has a doubt? Anybody who has a doubt? Anybody who has a doubt, please ask. So I'm assuming nobody has a doubt. So Palash, can you kindly move to the next slide? So now, do you realize that there will be identical subproblems? Who can say that there will be identical subproblems? What will be the identical subproblems? Yeah.
so
whenever X and Y match, Xi and Yj match, Xi and Yj will match at various places because you are doing, in one case you are removing from X, the other case you are removing from Y. So if you remove from X and then remove from Y, and you remove from Y and then remove from X, you are going to get an identical subproblem, isn't it? Are you not going to get an identical subproblem there? Yes or no? Is it clear or not?
So do you mean to say that, like, for instance, with the hello and the yellow, first we will remove H and then we will have yellow and yellow, and then we'll have to remove Y and we'll compare. But in the first fall itself, we had to remove then we'll again remove H and.
Right. See, when you have hello and yellow, okay, when you have hello and yellow, then H and Y do not match, do they?
No, sir, they don't.
H and Y do not match. So you will call it recursively on ELLO and YELLOW on one side. The other you will call it recursively on HELLO and ELLOW. Two of them you will call, correct?
Yes.
And in one of them where you have called it on ELLO and YELLOW, there again Y and E don't match. So you will again remove Y and you will get ELLO and ELLOW. The one where you had HELLO and ELLOW, again H and E don't match. So there again, so you will get from two paths, you will get an identical subproblem on that side. Is that now clear?
Yes, sir.
Anybody else still has a doubt?
Sir, can you repeat it? I didn't get it.
Yeah. So let me try once more to see. Palash, can you stop sharing the screen once? Let me see if I can share now.
Yes, let me do it.
Let me see if I can share the screen for a moment. I tried to reboot everything, but I'm not sure if it still works. It seems it is going to work. It's working right now?
Yes, sir.
Yes, you can see.
Good.
Yeah.
I had a question regarding the tree which we had in the previous problem, the KFM.
This
so
one?
You said.
This one?
Yes, sir. Yes, sir.
Okay.
So you have mentioned in the corner that we can pre-process it in order M, but I could not understand how we can pre-process it in order M, because I thought it would be order M squared, because we'll again have to traverse the entire length of
Yeah. So
P
there
and
is
see
a.
where.
I agree. An obvious algorithm is M squared, but there is a there is a good algorithm to do that. And in any case, normally M is supposed to be small compared to N. So we are more interested in managing N. Is that okay? I'll come back with a fast pre-processing algorithm also. So just to come back to this question. So somebody said how it will happen, right? Isn't this the question? Who had asked this question? How it will happen? Who wanted an explanation?
Sir, me.
Good. So we had HELLO and we had YELLOW. Now here the first XI YJ don't match, isn't it? XI and YJ don't match. So I will call this on two ways. One will call it on ELLO and YELLOW. The other will call it on what? Tell me.
HELLO and ELLOW.
Now here in this one, again E and Y don't match. So I will generate two of them from here. One will be LLO and YELLOW. The other will be ELLO and ELLOW. Up to here is clear?
Yes, sir.
Now here again in the right side, this one, HELLO and ELLOW again don't match. So H and E don't match, so I'll generate two. One will be ELLO and ELLOW. The other will be HELLO and LLOW. Are you clear?
Yes, sir.
So now can you see identical subproblem, this one and this one?
Yes, sir. Now I understood, sir.
Good. Very good. Anybody else still has a doubt about how identical subproblems will arise? So what will I memorize?
Indexes from that to that. If
I
it's
will memorize the array Lij, which I have depicted here. I will memorize the array Lij, which I have depicted here. Correct? So the rows 0, 1, 2, 3, 4, 5, there are 5 rows. This corresponds to null, nothing has happened. Then H, E, L, L, O. And the columns again 0, 1, 2, 3, 4, 5, 6. This corresponds to null. This is for Y. This is for E. This is for L. This is for L. This is for O. This is for W. And I will put in the values of whether what is the result here. So when one side is null, these are all zeros. And the other side is null, these are all zeros. Now I will check at this point. At this point, what am I going to check? Can anybody tell me what am I going to check at this point?
The longest subsequence if we consider the previous.
So I first check whether this matches with this or not, isn't it?
Yes, yes. Oh, yeah, yes, sir.
And if it matches, then I will call it on which side? Left, right, or which side? If these two match, then that means this case is satisfied. And because this case is satisfied, it goes on to this side or this side, or
We got diagonal.
Diagonal. Diagonal.
Yeah.
It goes on to the diagonal. So at any point, I will be able to maintain how many matches that have occurred till now. For example, here I know one match has happened. Here I know no matches, no matches. So at any point in time in my cell C, I will check which cells to find out what has happened. I will check this cell, and this cell. And if the element matches, that means the ith and the jth element matches, then what am I supposed to do? I will take whatever is in the diagonal plus 1. Or I will take the max of the left side and the right side. That is what is happening here, isn't it?
So why will we be taking the max of that and this? So could you please explain?
This is the max, no? I from here, okay. From here, wherever I am from here, I will get some optimal solution from here onwards.
Yes, sir.
All right. I will get some optimal solution from here onwards. Now, whatever is the solution from here onwards, let that solution answer be P, T. Now, how much will I add to T? I will add either the diagonal plus 1 or what will I add to T? Whatever I get back from the rest of it, what am I going to do with that? This is what will return, na? This is what will be returned. Not clear? Okay.
So I'll try to read it up again.
Okay. So now, no, I'll others have not understood or not? Others?
So not totally clear, but I think on second read, it will be good.
Okay. So then
so like how are we making the table? What is the significance of the boxes and
Okay. Okay. So
when we move, I believe understand what we're doing, but when we move horizontally or vertically, what we're doing is somewhat unclear.
Okay. I'll come. Let's do it once. Let's do it once. Okay. Are we okay here? All of you?
Yes, sir.
Okay,
Yes.
very good. Now, let us look at my recursion. What does my recursion do? My recursion says that if suppose here I am here, okay? Suppose I am here and I have found the solution here. So suppose the solution here cost is C. If the solution cost here is C, that means I have found a solution cost here C. Now tell me what will be the solution cost here, here, here. How will I find if I found the solution cost? Okay, so let me ask you another question. How will I find the solution cost C? From which elements will I find the solution cost C? From which cells will I find the solution cost C? Which are my recursions that I'm going to call at any point? Let me ask you another, make a more general stuff. I am at a point, I'm going to call my recursion here. This is Yj, this is Xi, and I am going to call the recursion here. What am I checking? Can anybody help me? What am I checking?
Xi equal to 1.
If Xi is equal to Yj, then the value of this cell is which value? It is which value? Look at the equation. If it is equal, then I call it an Xi minus 1 Yj minus 1 plus 1, which means I'm going to take it from the diagonal, isn't it? Yes or no?
Yes, sir.
So then it will be Q plus 1. And if it is not, if Xi is not equal to Yj, then it will be what? Then see, then R, let this value be R. Sorry, T. So here T is this. And if Xi is not equal to this, then T will be what? What are the two recursions that you call? These are the two recursive calls, hai na? Yes or no?
Yes, sir.
So one of them will come from which place? One of them will come from here, the other
P
will
plus
come
1 or R plus 1.
max of P or R. If this cell value is P, this cell value is R, this cell value is Q, then the value of T will be determined if Xi is equal to Yj then t will be q plus 1. If xi is not equal to yj, then t will be max of p and r. Are you all convinced now? Ishan?
So just one question. The reason why we're going from Q to T, that is from the higher index to the lower index, that is because we're if we know that till this point so many elements have matched.
Okay. Let me do it again. Let me do it for all of you again. This is xi, this is yj. So now which is xi minus 1 plus 1, what? Which is the element? So this is xi, this is yj. So this is xi plus 1, this is yj plus 1, है ना? Are you all okay with me?
Yes, sir.
So now what am I checking? I am checking if xi is equal to yj. If xi is equal to yj, what am I calling? This person?
Yes, sir.
I'm calling the next person or no? Or previous person. Which one are you calling? We had
Next person.
hello and yellow. So if H and Y don't match, then if this is hello and this is yellow, then one of them, so there are three possibilities. So let this be three possibilities can get generated. One is yellow and yellow. If these two had matched, suppose this is xi and this is yj. If these two had matched, I would have looked at this one. Yes or no?
Yes, sir. Yes, sir.
Which is this place? Which is this place? Otherwise, I will look at this one and this one. है ना?
Yes, sir.
So to get the value of t, if xi is equal to yj, and as I had written here, this is p, whatever I had written, this is q, and this is r. If xi is equal to yj, then t is equal to q plus 1. Whatever is the value of t will be whatever is the value of q plus 1.
Yes, sir. Yes, sir.
And if it is xi is not equal to yj, then t will be max of r and p.
Yes, sir.
Has others understood?
Yes, sir.
So that is what I'm saying. If I memorize, that is what I said here. If I memorize this array Lij and I call it recursively, I will check if Li plus 1 j or j plus 1 I, whatever I'm doing, whether it is already done or not. If it is done, I will not call it recursively. And if it is not done, I will call it recursively. And I will compute the value based on this formula. And this formula is identical to this formula, whatever we have done here. If it matches, I add 1. If it doesn't, I add 1 from the diagonal element. If it does not match, I take the max of the two elements on the two sides, left side and bottom. Is it now clear?
Yes, sir. Perfectly clear.
So what is the complexity of this algorithm now? order
NM.
N. So this gives me an order NM algorithm where I have remembered all the elements. Now, what can I do? I can compute this iteratively. Now that I know how to do it, I can start from here and compute it iteratively from one side. Or I could start from the top and this side and compute it. I can now compute it in any direction. The top down was computing it in the direction like this. The iterative algorithm could also compute it in the direction like this. How will it compute it in the direction like this? It will just do the same thing. It will check on an element, it will check the top, left and diagonal and add or not add. So how will it work? It will assign all of them to initially 0, the rows and the columns. So now I could have done it in the normal recursive form where it would have gone from this side upwards. And I can do it also from the diagonal, which I can do it in this way. How do I do it? I first fill up the first row and the first column, all zeros because they are all nulls. And then I only need to check what? I need to check whether any element is matching. For example, H and Y do not match. So now I'm doing it in the reverse direction. So I will take it the max of this and I will get 0. Now I have to fill up this cell, all of them will be 0. The first cell where there is a match is this E matches with this E. So what will it take? It will take whatever was in the diagonal plus 1. Then on every side it will move either this way or in the diagonal. Why does this increment? Because L matches with L. So this becomes 2. Now you can get a match in many directions. Then this from 2 becomes 3. Now look at this case. This is L and this is O. We know that the matches till now, the best match till now, I am looking at this cell, L and O cell. The best match till now is 3. And L and O do not match. Therefore, I cannot add 2 plus 1. So I have to take it from the maximum of the left and the top. So this is a simple way in which I convert the recursion to an iteration. Anybody has a doubt here? In the previous case, I did it from the bottom. Now I am doing it from the top down, left to right, top to down. This is the iterative version. Whereas in the recursive version, you calculate the bottom stuff and move from bottom to top and right to left. That is what we had seen when we did this. The top-down algorithm starts here and moves in these directions by the recursive calls. Whereas the reverse algorithm, the iterative algorithm could have done this as well. It can also start from this direction and move backwards. So how to write the iterative algorithm? The iterative algorithm is therefore now written this way. I have a double loop for I equal to 1 to n, j equal to 1 to m. I initialize this. Otherwise, I move like I move in Pascal's triangle. I move for every row, for every column, I just need to check if xi is equal to yj. Then I pick up what is Lij minus this. So this is the bottom up algorithm. Minus plus to sab गड़बड़ कर दिया हमने. This should be j plus 1. Na? I have started from I equal to 1. This is 1, 2, 3, 4. So this should have been. So yeah, right. Lij I will pick up from the if. Are you all lost?
No, sir.
Okay. So if xi is equal to yj, I will pick it up from the diagonal, previous diagonal. So here this algorithm is working like this. It is moving row wise, column wise. So for it is going through every row and then every column. And then for any cell here, it is checking if xi is equal to yj, then it is picking it up from here. If it is not, then it is picking it up from the max of these two. So I have now converted my recursive algorithm to a simple iterative algorithm, which again takes that same amount of time and the same amount of space. Because at every point I am doing only one constant time computation. So here, by remembering everything, by converting it into an iteration, I have now got the longest common subsequence problem solved faster. Any questions? Anybody has any questions? Divyansh? There are two Divyanshs. Divyansh, do you have any question? Abhishek? Abhishek Gurjar?
No, sir.
Okay. Anybody has a question? Fine. So having done this, we now generalize the idea, and the generalization of that idea is a straightforward concept. The generalization of the idea comes from the fact that we can assign costs. So what am I trying to say is that if they match, I will give a cost for matching. If they don't match, then what am I doing? So there are three cases that I am doing. One is match. So there is a cost for matching, maybe 0. And if they don't match, then I take two paths. One I call delete from X. The other I call delete from Y. And when they match, I delete from both. This is my recursive in LCS. In LCS, my recursion is if they match, I delete from both. If they don't match, I delete from Y. If they and I delete from X and delete from Y, and I take the best of the two. But if I assign costs, then I can assign costs for deleting from X or deleting from Y. And for match, I can assign costs. So the deleting, I can also insert a new element. So the generalized edit distance says that I will have costs for matching, I will have costs for inserting a new element, I will have costs for deleting an element, and I will have costs for substituting an element. So now, by this insert, delete, substitute, I transform a pattern P1 to a pattern P2. So how do I take one pattern and transform it to another pattern? So how do I do that? Suppose I have started from yellow and I want to reach hello. Then what are my options? At the first point, I can delete Y. Then I can insert H. Or instead of deleting Y, I could have substituted Y by H. Then E and E will match. Then L and L will match. Then O and O will match. And then I can delete W. So I can do this by one substitution plus one deletion. I will reach from yellow to hello. If I have to reach from hello to yellow, then I can either substitute H by Y and then I will get, sorry, I have to substitute H by Y, then L, L, O, and then I have to insert W. So I can do a substitution plus an insertion. This sort of costs, that is, so they will assign cost for insertion, cost for deletion, cost for substitution, and cost for match. And if they assign such costs, what is my objective for this transformation? My objective is to find what? Find the minimum cost changes that I have to do to convert one string to another. So I have to convert a minimum cost string from one string to another with minimum cost. So this is what is called the edit distance. This is what is called the edit distance, the distance from one string to another through match, insert, delete, and substitute. For example, in this example, if I gave match cost 0, insertion cost 1, deletion cost 1, and substitution cost 2, then I know that, like I have done here and I have done here, I can convert one to the other in cost 3. If I gave insertion, deletion, and substitution, all of them cost 1, then what will be my new cost for conversion of hello to yellow or yellow to hello?
So 2.
2. Then it will be 2. So all this spelling error checks and things that we do, they try to find the word with closest edit distance. And then they try to tell you that this is the word that we need. So the problem of longest common subsequence and finding the minimum cost edit distance are almost similar problems. So the recursive definition is also almost identical. But here, since we have insert, delete, and substitute, and we are assuming that match cost is 0, just like in common subsequence, for Dij is equal to D minus 1 J minus 1 if Xi equal to Yj. Otherwise, I do I minus 1 J plus delete cost I j minus 1 plus insert cost and I minus 1 j minus 1 by substitution cost. And I take the minimum of them. And once I take the minimum of them, then I get my recursive definition. And because I get my recursive definition, I have now in a position to do exactly whatever I did, whether I do a top-down or a bottom-up algorithm, for finding out the minimum cost edit distance between two strings. So the longest common subsequence, its alter ego or a more generalized version is called the edit distance. And the algorithm to the recursive definition, the memoization and everything else are identical. And therefore, that is why it leads to the same complexity algorithm. If you watch my other video, I have worked it out in details out there. So you can watch it and you can read any book where all this is given. Any questions? Anybody has any question? Or Kadeep?
So,
yeah.
Yes, there's no questions.
Okay. Yes, Ishan?
So I had a question, but I would prefer to ask it after the recording is stopped. So like it's a very general question.
Yeah, tell me.
So when you had asked us to write down the pseudocode for the longest common subsequence problem, instead of defining it the way you did, I took a different approach, which was which I thought was a bit more optimal than what we were discussing. But then by the end of it, I realized that this is a lot more optimized than what I was thinking of.
You share it with me later on. I will have a look at it.
Yes, sir.
Okay. So there are more variations. Variations mean, we did not allow exchange. Many of your typos, if you note down, your typos are like this. THOUGTH, isn't it? When you type down, your typos often get interchanged. So how would you allow costs for exchange? Because that is a common mistake. So that is a very interesting thing. Then how would you allow, when it comes to three strings, what is the longest common subsequence of three strings? And obviously it is not, if you do it pairwise, you won't get the longest common subsequence of three strings. Is it clear? Arunendra? Mayank? Omi? Aditya?
No doubt, sir.
Are you clear that if I want to find the longest common subsequence of three strings, if I take them pairwise, I may not get it?
No, sir. Like if you take it pairwise, you'll get different subsequences common. Like and like you won't get the longest possible one.
Right. So this multi-dimensional matching or alignment is another problem. And when you have very large strings, then how to do it in an approximate manner is another question. That means when your strings are of billions of size length, then even an order m plus n algorithm is not good enough, because that will take a few months to solve or maybe a few years to solve. So you need to find faster than that. And most of the algorithms in biology have billions of strings to be matched, aligned to each other. So there they find out approximation solutions, not the optimal solution. Okay, we'll stop today. I'm sorry for all the disturbance with power cut and machine failure. If you have any more doubts, we will again discuss on Thursday when we do our tutorials. But still, you can stop the recording now. If you have any other questions, I'll be happy to answer. Anybody